Okay, let us begin the final lecture on standard model theory, also known as quantum field theory 2, since the lectures have been unified. And we are in the middle of discussing charge universality and the charge renormalization in the standard model. As we have discussed in QED, that is rather simple by means of one particular Watt identity, which is well known and easy to prove and establish. Whereas in the standard model, we have to disentangle the two phenomena, namely charge universality on the one hand, the physical statement for S-matrix elements evaluated on-shell, and the simplification on the renormalization constant delta E.
طيب بسم الله الرحمن الرحيم. أنا أود أن أنبه إلى شيء معين ذكرته في الفيديو أحد الفيديوهات السابقة، أن كمية التحرك هي صغيرة، ثم عندما تصل حدود الأونشيل اللي هي بي تربيع يساوي ام تربيع، هنا ستكون كبيرة مساوية لام تربيع، وهذا ما يؤدي إلى التحلل. لكن هو على ما أعتقد هو العكس صحيح، كمية التحرك كبيرة، لأن ذكرنا أن الكتلة صغيرة كل ما تعمقنا في التفاعل، وكتلة صغيرة والطاقة كبيرة، كتلة صغيرة والطاقة كبيرة. ما يحدد الطاقة حسب الكتلة هو الفضاء ربع الأبعاد. طيب تعال نرجع لمعادلة تاني، لأن هناك تصحيح أريد أن أفعله. نجرى إلى هذه المعادلة. هذه المعادلة تعبر عن النسبية الخاصة اللي هو MC سكوير على GM سكوير M كابيتال العامة أو الجاذبية. فنجد أن النسبية الخاصة في البسط والنسبية العامة في المقام أو الجاذبية في المقام، وهذا يعني كلما زادت M في المقام يجب أن تزيد MC سكوير. إذن التصحيح الذي يريد أن أقوله أنه داخل التفاعل كلما تعاملنا على التفاعل تزيد MC سكوير، وهنا ينكسر التناظر في معادلة E يساوي MC سكوير، ينكسر التناظر بحيث تزيد C سكوير وM تظل ثابتة أو تقل. هنا التناظر يكسر، وحيث أن تبلغ السرعات ممكن تبلغ السرعات أكبر من سرعة الضوء حسب شدة طاقة التفاعل والمسافة التي يحدث فيها التفاعل، وهذا ينطبق على البي اللي هو كمية التحرك. كمية التحرك أيضا تكون عالية عندما تبلغ الجسيمات الناتجة من التفاعل تصل إلى الأونشيل. هنا تتدخل في النسبية الخاصة بقوة، لأنها تتحكم في الفضاء ربع الأبعاد. فالفضاء هو الذي يتدخل، فضاء ربع الأبعاد الذي نعرفه، فهذا الفضاء يفرض على الجسيمات أن تطيع النسبية الخاصة E يساوي MC سكوير، وبالتالي إذا وجد أن الطاقة أعلى من الكتلة تحلل، يعني الطاقة أعلى من الكتلة بC تربيع تحلل مباشرة، تتحلل الكتلة مباشرة. طيب أثناء خروجها هذه الكتلة، أثناء خروجها من التفاعل أيضا تظهر فيها خصائص النسبية الخاصة بقوة، بحيث أن هذه الكتلة تبطئ هذه السرعة العالية، فإن الكتلة تتضخم كلما ذهبنا من وسط التفاعل إلى نهاية التفاعل اللي هي الكرة التي عبارة عن B يساوي M سكوير. هنا ما يحصل هو أن الطاقة العالية التي أدت للسرعة العالية والكتلة الضعيفة تقوم بتبطيء هذه الطاقة العالية. تقل الطاقة العالية كلما ذهبنا إلى نهاية التفاعل، والفضاء رباعي الأبعاد يحاول السيطرة على الفضاء، أو السيمتريس تحاول تسيطر على الفضاء. في نهاية التفاعل أيضا الكتلة M تضخمت ذاتها، لكن بطريقة بسيطة جدا. الانتقال من B يساوي B تربيع يساوي M تربيع إلى الفضاء رباعي الأبعاد الذي نحن بنستطيع أن نعرفه، هذا الانتقال تسيطر فيه هذا الفضاء رباعي الأبعاد تسيطر فيه السيمتري بقوة، وبالتالي أي طاقة عالية تتحلل مباشرة تتحلل. لهذا نجد أن الزي والدبليو طاقاتهم عالية، 90 جيجا و80 جيجا، هذه طاقة عالية وسرعة عالية طبعا، وتتحلل مباشرة إلى جسيمات وليدة. نجد أن النيوترينو يخرج من التفاعل لا يتحلل. نجد أن الإلكترون يخرج من التفاعل لا يتحلل. الجسيمات التي خرجت من التفاعل لا تتحلل، لكن الجسيمات التي طاقتها كبيرة وخارج من التفاعل هي التي تتحلل. وأعتقد أنه التعديل سيكون في الفيديو أحد الفيديوهات رقم 36، إما A إما B إما C إما D. أعتقد أنه C أو D، واحد من هذه الفيديوهات. أرجو إلحاق هذا التعديل، وأرجو التأكد من صحة هذه الفرضية، ليس التعديل فقط إنما التأكد من صحتها في التجارب.
Working on charge universality, and we have studied the properties of Landau gauge, which is a special gauge where the gauge parameters are 0, where the ghost masses are 0, and where the gauge fixing term does not involve ghost interactions with the Higgs, but only with vector bosons, and the vector boson propagators are transverse, and therefore many loop diagrams actually vanish. In particular, we have found the so-called anti-ghost equation, which tells us that at 0 momentum there are no loop corrections involving ghosts. And as a result of this, we can now go back to the actual proof of charge universality. Namely, we use Landau gauge plus the on-shell renormalization conditions plus the Slavnov-Taylor identity. So, and now we directly start by writing down the appropriate Slavnov-Taylor identity which governs charge universality, which is really the analog of the Watt identity of QED. If you are experienced with Watt and Slavnov-Taylor identities, then you will immediately see the similarity. Namely, we take the Slavnov-Taylor.
انظروا، أنا أريدكم أن تلاحظوا أن السلافنوف identity تعمل في أو يعتمد عليه اعتماد كلي في المساغ الخاص بالأونشيل، والتي تفسر اللوبس interactions أو اللوبس اوردر. في الحقيقة الاعتماد على هذه الايدنتيتي يسري مفعوله تمام في ظل فضاء رباعي الأبعاد. حتى داخل الفضاء ثنائي الأبعاد ما دام ليس هناك صراع فالايدنتيتي تعمل بكفاءة ما دام ليس هناك صراع. لكن في حالة الصراع اللي هو داخل التفاعل، عميقا داخل التفاعل، كما ذكرت أن الايدنتيتي لا تعمل، وبالتالي فقط عند بي يساوي بي سكوير ساين ام سكوير اللي هو انشل هنا تعمل الايدنتيتي، والايدنتيتي تعمل بطريقتها صحيحة ان بي في حين فقط ان بي يساوي ام سكوير. طيب ماذا يحدث إذا كانت داخل الايدنتيتي؟ هذا ما كنت أريدكم أن تلاحظوه في الفيديوهات السابقة. فربما تحدث عن هذا الأمر، ماذا أريد أن أقول؟ لاحظوا في الفيديوهات، أعيدوا الفيديوهات مرة أخرى ولاحظوا تتبعوا هذه الايدنتيتي وحاولوا أعملوها في داخل الأونشل قبل أن تصل بي يساوي ام سكوير، وأيضا في حالة الضوء قبل بي يساوي زيرو، بي عندما تكون أعلى من زيرو. يعني ماذا تفعل الايدنتيتي وكيف تتصرف الفيزياء هناك؟ أنا سأحاول أعيد الفيديوهات إن شاء الله بيني وبين نفسي، يعني هذه الفيديوهات سأنشرها هكذا، لكن سأعيد هذه الفيديوهات دراسة بعمق، ثم بعد ذلك إن شاء الله تظهر هذه الدراسة في فيديوهات قادمة، سلسلة جديدة وأوراق علمية قادمة إن شاء الله. لكن ما أريدكم أن تلاحظوه أن الاستثناف identity لا تعمل عميقا داخل التفاعل، وهذا ما يعطينا اختلاف في الكتل، فهي تعمل عند بي سكوير يساوي ام سكوير، تعمل بشيء جيد، وهذا وضع الاستقرار، فإن هذه الايدنتيتي تعمل بشكل جيد. في عدم الاستقرار كل سيمتريز مكسورة، اللي هو في ظل الصراع بين الكتلة والفضاء ثنائي الأبعاد، كل سيمتريز مكسورة. فضاء ثنائي الأبعاد سيكون أهمه الأقصى هو طرد الكتلة أو الطاقة الزائدة، هذا هو الهم الأقصى. بعد ذلك عندما تصل الحد اللي بيساوي ام سي ام سكوير، بعد ذلك تستعيد السيمتريز وتظهر تأثير ميكانيك الكم اللي هي تظهر تأثير الكيو اف تي، يسترجع النموذج المعياري سيطرته وتحليله وتنبؤه بما يحصل، وهذا ما جعل النموذج المعياري غير قادرا على التنبؤ بالكتل بالرغم من المعجزات التي ذكرها في الفيديوهات السابقة. النموذج المعياري لديه معجزات سماها البروفيسور بميريكلز. هذه المعجزات تعمل، بالرغم من هذه المعجزات لم يستطيع النموذج المعياري التنبؤ بالكتل وتحليلها إلا في ظل هذه الايدنتيتيز. لكن الآن يحلل الشحنة، وحتى الشحنة التحليل هو صحيح في حالة الكوركشن لوبس، لكن في داخل التفاعل، عميقا داخل التفاعل ليس صحيحا، لأن الشحنة تزيد. ربما تظهر في هذه الكوركشنز أنها تزيد، ربما ذلك، لكن كلما صارت الأبعاد الشحنة أيضا تزيد مع زيادة الكتلة. طيب نواصل.
Identity and take a third derivative with respect to the photon ghost and with respect to two fields psi and psi bar, which could correspond to any charged fermion or even to a charged scalar. Doesn't really matter, but we will work for fermions. And then we set the fields to 0. What does it mean? The derivative with respect to the ghost corresponds to the gauge transformation in QED direction, so it corresponds to an identity which tells us something related to gauge invariance of QED and a massless photon. And then this is here similar to the Watt identity of QED between the electron self-energy and the three-point function between electron, electron, and photon. And that was exactly the Watt identity needed in QED to prove charge universality, and so this is the analog of this. Doesn't really matter, but we will work for fermions. And then we set the fields to 0. What does it mean? The derivative with respect to the ghost corresponds to the gauge transformation in QED direction, so it corresponds to an identity which tells us something related to gauge invariance of QED and a massless photon. And then this is here similar to the Watt identity of QED between the electron self-energy and the three-point function between electron, electron, and photon. And that was exactly the Watt identity needed in QED to prove charge universality, and so this is the analog of this. And now we simply need to work out what comes out of this equation in the standard model, and you will see the complexity right now. So what are all the fields, all the terms which actually do not vanish? So as always, we have this structure. Products of two gammas, and we have one field and one source. So for example, one term that could contribute is this one here, where we have the source of the photon, and then we distribute these three derivatives in an appropriate way, for example in this way. Okay. Then we have here the three-point function between electron, electron, photon, and a prefactor, and that prefactor corresponds to the gauge transformation of the photon, which is the derivative of the ghost, and from this we will get a factor p mu, momentum p mu. So that will immediately give us the contraction of the momentum p mu times the three-point function, which was the essence of one of the terms in the QED Watt identity. Very nice, but it goes on. So then the photon mixes with a Z. It has the same quantum numbers. Therefore, whenever there is a photon term, there is automatically also the same term with a Z. And also both of them mix with the Goldstone boson, because even that has the same quantum numbers. So there is also a third term where we have here the Goldstone boson neutral. And then this. And then what else can we have? We can have other contributions. For example, we can have a derivative of gamma here from the Schaffner-Taylor identity with respect to spinor fields, psi. And then we have here k psi. And then we can distribute those three derivatives as follows. So here we can get the psi bar. And here we get the psi and the ghost Ca. Plus gamma psi and psi bar reversed, psi bar, k psi bar, gamma psi bar, psi. And so we need to be a little bit careful with the signs of the expressions. And maybe let me correct that. So like this. And like that. And then we should have always an even number of fermion reorderings. Yes. Okay, so this is the Schaffner-Taylor identity, and you see this term is exactly equal as in QED. except that the prefactor is not just p mu, but it contains a loop correction. But somehow it is related to p mu. Here there is the electron self-energy, also electron self-energy, but they are again modified by prefactors which receive loop corrections. And in QED we simply had here p mu at all orders, and the prefactors were also fixed at all orders to be equal to the charge. And then in QED we would get p mu times the 3-point function gives a difference of 2 electron self-energies times the charge. And then at p equals 0, this 3-point function is equal to the derivative of the electron self-energy. That was simply the QED relation. And now we have all the loop corrections in the prefactors, and we have additional terms from the mixing with the set and with the unphysical Goldstone boson. And that is the difficulty. And here comes into play Landau gauge, because in Landau gauge we are now able to evaluate all the prefactors, and that is where the simplification comes in. And so let us now do that. So what happens around momentum p of the ghost Ca approximately 0? So let's see. So the this term here was exactly the one that we discussed at the end of the previous lecture, namely that must have been of the order p to the 3rd power. That was the consequence at the end of the last lecture. So we have here a Lorentz index, so clearly it is proportional to p mu, but actually it must not only vanish proportionally to p mu, but to the 3rd power of p. And so therefore the second term is proportional to p Ca square times p Ca mu, vanishes with the 3rd power of p. What about the third term? The third term here, that is also what we said. The mixing between the Goldstone and the QED ghost is 0 at 0 momentum, because it's 0 at 3 level, and because of there are no loop corrections, therefore it remains 0 at all orders. And so this is a scalar, so if it's 0, then it behaves as p square at least. So the third term is proportional to at least p Ca square. Therefore, in the limit where this ghost momentum is small, we can immediately drop those two terms which are really the specific standard model terms coming from the mixing. So the Z and the Goldstone can now be dropped. And at first order of p, we only need to look at these QED-like terms, namely these 3, which are the ones that also appear in QED. And then what is left to be done is the loop corrections. So therefore let us drop these terms. And then let us do the following, like in QED. We take the derivative with respect to this ghost momentum of the whole expression and evaluate it afterwards at ghost momentum equal to 0. Then that means we take the first order term of p square, of this p. So what happens in this way? Then we get here the following. First of all, that is proportional to p. Therefore, at first order in p, we get only the derivative from here. We do not get the derivative from the second factor, but only the derivative of the first factor, because that is linear in p. And that derivative gives us some constant factor. We don't know which one, but it is a constant. And this constant depends only on this green function, which is universal. There is only one such green function. It doesn't depend on the charged particle in question. Times this interaction at which momentum configuration? Let's say minus p, p 0. So the 0 here of the photon corresponds to the fact that we have set the ghost momentum to 0. By momentum conservation from here to here to here, this is now the 0 momentum. So we get this. Then the second and third term are dropped. And then in the third term, in the last line, what do we get? We get at ghost momentum equals 0, what we said before. So this green function at ghost momentum 0 is equal to tree level. That was the point. So this is equal to tree level, and therefore we get simply the tree level result of one of those terms times the first derivative, and that is actually p independent. First derivative with respect to the electron momentum now, psi bar psi minus p and p. So here we also use momentum conservation, like p prime is equal to p plus p ca, and then let's keep this p prime constant, or p is constant. And p, so the derivative with respect to the ghost momentum is equivalent to a derivative with respect to one of the electron momenta. So in one of those terms the momentum is kept fixed, and then this term vanishes with the derivative, and in the other term we get exactly this. And then we have exactly a sum of two terms which is completely analogous to the structure in QED. Constant times 3-point function evaluated at this momentum configuration is equal to another constant which is governed from tree level times that. And so now let us go on. We have not yet used on-shell momenta, but now we can also use on-shell momenta. So we can go to on-shell momenta. So where this momentum here for the electron or whatever fermion self-energy is on-shell, then we know that we have required on-shell renormalization conditions for this. So therefore, if we evaluate everything between spinors u of p, u bar of p and u of p, then because of the on-shell renormalization condition, this again becomes equal to tree level. All the on-shell conditions basically mean that these 2-point functions behave as at tree level at on-shell momentum. So therefore, this becomes also equal to the tree level result. And therefore, evaluated between spinos u bar and u, and evaluated for on-shell momenta and zero photon and ghost momenta, we get the final relationship which I write down here, namely u bar of p times the 3-point function gamma psi bar psi a mu at momentum minus p, p0 u of p. This relationship is equal to some non-vanishing constant times the tree level result. So this is the relationship. So this object here is equal, so I should say on-shell. Because basically this factor is now tree level, this factor is equal to tree level, this is the constant, and therefore we can solve this is equal to its tree level value. Right? So there are no loop corrections. And that applies for the fermion psi that we have chosen, but we have not chosen a specific fermion. The derivation works equally for all fermions, and therefore this is true for all charged particles or charged fields psi. And that means that our relationship that we wanted to prove and that I outlined in the morning is really true, namely the effective on-shell interaction of any charged particle with a photon is equal to some universal constant which doesn't depend on the matter field times whatever you prescribe it to be at lowest order. And what do you prescribe it to be at lowest order? It's the electron charge times Q, where Q is this quantum number T3 plus hypercharge. That is the claim. So once you fix those quantum numbers, by writing them into the Lagrangian, then for these on-shell values, there are no loop corrections at all. And simultaneously, this is the case for all charged particles. Therefore, if you now satisfy an on-shell renormalization condition, where the condition would tell you that this, for the electron specifically, by definition is equal to the electron charge times the tree-level result, then you know from this simultaneously the same is true for all other charged particles. They all will be equal to the electron charge times their respective tree-level results. And so this is the universality of the electric charge, which is this important property of QED, and we see here that it holds in the same way also in the standard model. But because of the non-abelian nature and because of the mixing, it is much more complicated. So the non-abelian nature comes into play in the loop corrections, which in principle are there in those prefactors, but they are absent in Landau gauge, and the mixing comes into play here, which we can also control in Landau gauge. All right, so this is this important physical statement. Let me clean the blackboard and remove this French language stuff. Right. Then we can go to the second topic, which was applying this to simplify the renormalization constant for the electric charge. So that is then charge renormalization. And here again, surprisingly, there is quite some literature on this, and you can in exactly the references that I have already mentioned many times. And let me present you the latest progress on this, which is probably the ultimate simplification of charge renormalization, the most beautiful, let's say, approach, which in the simplest possible way gives you the most powerful possible answer. So that was really ingenious progress by Dittmeier, I would say. How do I write this? Ingenious idea or trick by Dittmeier. And as you see, sometimes, though not always, the simplest ideas are sometimes the best, even though it doesn't always work like this. But in this case, the idea is to use a test particle, you know, from high school or from first semester classical mechanics, where you have all these test particles in the gravitational field of the Earth, so not to disturb anything, or test particles in electric fields and so on, so with very small mass, very small charges and so on. And surprisingly, you can use the idea of test particles also in renormalization theory. And so here we introduce a test particle into the standard model, which almost doesn't change it, which is an infinitesimal addition to the standard model, which is only there to, let's say, give us some information on the renormalization structure. And by this trick, we can, in an extremely simple way, get the information that many people before, including the same people, have struggled with. So let's say this is the idea of a test particle. He calls it differently, but anyway, so the idea is to introduce a new fermion, let's call it eta, which has the following properties. It is a Dirac fermion. Dirac fermion means that it has equal left and right-handed charges. Therefore, we do not have to distinguish left and right-handed parts of it in the Lagrangian and in the interactions. And most importantly, it does not give a contribution to the gauge anomaly, because only chiral fermions can contribute to gauge anomalies. Therefore, the structure of the standard model cannot change in a significant way by adding such a Dirac fermion. Then it is an SU2 singlet, just to make it simpler, such that the generators TA are 0, and it has, let's say, hypercharge equal to electric charge q eta for a singlet hypercharge and electric charge are equal. And so let's call this charge q eta, and let's treat this as infinitesimal. That is the idea. And then there are no interactions with anything except what? And maybe this is a small exercise for you. So if you add such a fermion to the standard model, what could be the possible gauge invariant terms in the Lagrangian, and what are the possible resulting interactions of such a particle and field with all other particles which exist? So I will add here one line which interactions exist, and so you might say that the standard model Lagrangian gets the following additional terms. So what are the additional terms, or what are the possible interactions? So who has some ideas? Some idea? So kinetic term would need covariant derivative, and so we would have this eta, it is called I d slash eta, and the covariant derivative would be the one that it always is, and in this case there are no TAs, there is only hypercharge, and therefore indeed it interacts with a Z boson and the photon, but not with a W boson. And there is a mass term, minus m eta times eta bar eta. And that is gauge invariant because it is a Dirac fermion, so left and right-handed eta transform in the same way. Therefore, we can write down an explicit mass term for it. Question: can we also write down an additional mass term coming from the Higgs interaction, like a Yukawa term, where also the Higgs gives a mass to this eta particle?
Because we would have to couple it to some fermion doublet and the Higgs doublet, but then we have to check the hypercharge such as gauge invariant. We do not have a quantized charge, but we said it's infinitesimal.
Yep.
So therefore, I guess that if we
Right.
do it like this, we cannot cover something.
Exactly. So first, yes, right. It's exactly as you say. So in particular, the hypercharge can never be conserved, since no other particle has such a hypercharge which could add up with this to 0. Therefore, that's all. And therefore, the only interactions are photon and Z. Okay, but the standard model has charge universality. And charge universality clearly is not destroyed by adding such a fermion, because the proof, of course, does not know how many fermions there are in the standard model and whether they are Dirac fermions or non-Dirac fermions. The proof doesn't care about the nature of the fermions. Therefore, of course, it applies also to the eta. The eta is one of the fermions that we can use over there. Charge universality. So the on-shell condition for psi, for all psi, is equivalent to an on-shell condition for eta. That means we can now say that instead of applying and imposing an on-shell renormalization condition for the electron-photon interaction and computing our renormalization constant, we say instead of it, we impose the same on-shell condition for eta and then evaluate our charge renormalization constant, and then we know that it is the correct result also for the other on-shell conditions. And because of this infinitesimal charge, and because of these extremely simple interactions, computing the renormalization constant from the eta condition will be extremely simple. So what we need to do is to work out the renormalization procedure. So let us now really take the on-shell renormalization condition for the case of the eta fermion. And the on-shell condition for the eta fermion means that for eta being on-shell and the photon having zero momentum, all the loop corrections, including counter terms, must add up to zero. That is in words what must happen. And in order to do that, we of course now have to evaluate the one particle irreducible higher order corrections to that green function. So we need to write down what all these Feynman diagrams are. Which Feynman diagrams exist for this interaction? We can start with tree level. Tree level exists. And we know its value because it's unambiguously given by the charge. But how does it go on? There is, of course, counter term contribution. So this is a one particle irreducible contribution to this green function. And this renormalization constant contains delta E, among other things. And delta E is the thing that we want to determine. What else? In addition to this, we get actual loop diagrams. What are the actual loop diagrams?
You can, of course, exchange A or Z boson between the legs.
Yes. This Feynman diagram is proportional to q eta to the third power, because each vertex contains q eta, and this Feynman diagram is q eta to the first power. Now if q eta is infinitesimal, then this diagram is in some sense negligible. We might need to become a little bit precise what that means, but for that reason, you might wonder, are there maybe Feynman diagrams with fewer powers than q eta to the third power? So clearly there are Feynman diagrams with higher powers. So that, for example, would be q eta to the fifth power, and so on. Or such a Feynman diagram. Here it depends if this loop could be, for example, a top quark. Then this Feynman diagram contains 3 powers of q eta and 2 powers of the top quark charge, which is not infinitesimal. 3. But does anybody see diagrams which involve less than 3 powers of q eta? I would say that at least I can see some diagrams with 2 powers of q eta. Can anybody see a diagram with 2 powers of q eta? It is a good practice for you to think in terms of standard model Feynman rules, what kind of interactions exist. So you might, for example, start your line of thought from this diagram here. So this diagram contains 3 powers of q eta and 2 powers of the top quark charge.
Some idea what if we start from the photon line with something else that is not the eta, and then we just land at the eta line when we couple with the photon, and so we would just have 2 of these?
Yeah, okay, good idea. So let's try that. Actually, so it should look like this, and then here there must be a photon or a Z. So then we must connect this somehow. There is not a triple vertex where one photon goes into 2 other photons, but clearly there is, for example, what? A W boson loop, for example. W boson loop, and then this could be here a Z and photon, something like that. Indeed, very good. Q eta square. But I think it is quite obvious, without going into any further details, that there are absolutely no diagrams which are linear in Q eta. There cannot be any loop diagram where we have only one coupling to the eta line. The eta line must go through the diagram, and so if it's one pi, then the eta line must have for sure at least 2 couplings, and therefore every diagram except for those 2 must be at least order q eta square. So we can say it is equal to this plus that plus order at least q eta square. Very good. And so, okay, maybe not immediately very good. So what is actually the result of this? Let's write it down. This is minus I e q eta times gamma mu. And the counter term Feynman rule, I copy it from here, is minus I e q eta times delta E over E plus 1/2 delta ZAA. And plus the field renormalization constant delta Z eta for the eta field. And then there is this other term for the counter term coming from the mixing with the Z boson, minus I e divided by sine times cosine times minus q eta sine square times gamma mu here in all these cases. Gamma mu times delta Z ZA divided by 2 plus higher orders in q eta square. Okay, so this is the expansion, and now we can be precise. So we know for sure that at order q eta we have this expression. And then there are some additional terms which are all of the order q eta square or higher order in this term q eta. And I'm not even excluding that also these renormalization constants depend on q eta. Maybe they do, then part of this would also contribute to higher orders. But that is okay, so but this is a correct expansion. Then what we want is the delta E determination. And so delta E will now depend such that the whole sum of all the diagrams, including loops and including renormalization constants, have to vanish for the on-shell configuration. So one small thing is the delta Z eta. So delta Z eta is determined from the self-energy, which are such Feynman diagrams. this is the self-energy diagram for the eta particle. And so this is of course also q eta square. And so clearly there are higher order diagrams like this, which are q eta to the fourth. There are also diagrams which are only q eta, maybe with some W boson loop in the photon propagator as well. But again, here it is also obvious that since there must be an eta line in the Feynman diagram, it is clear that the diagram contains at least 2 powers of q eta. So therefore, delta z is determined from the derivative of this on shell. Delta z eta is of the order q eta square. Okay, and therefore we can now evaluate the whole idea, namely the on-shell condition tells us the following: 0 is equal to this expression here above at on-shell momenta, which is q eta times this delta E over E plus 1/2 delta Z AA plus, or then here, what do you say? This is minus sine divided by cosine times delta Z ZA divided by 2. So I can combine the delta Z ZA term with this, and I get this additional prefactor, sine over cosine of the weak mixing angle, and all of this gets corrections plus order q eta square. And so the delta Z eta has dropped out of the square brackets, and all the loop diagrams have also dropped out of the square bracket. So what we get in simple terms is that our on-shell condition is valid for every value of q eta, but therefore it's in particular valid at first order in q eta. And at first order in q eta, we only get a relationship between delta E and the field renormalization constants for the photon and the Z. And all the actual loop diagrams that contribute to the self-energy and all the actual vertex corrections which contribute to the process, they completely drop out because they are of higher orders in this q eta. And so this is this magic of the test particle trick. And so we completely decouple the non-trivial loop graphs from the simple formula which relates our delta E over E with field renormalization constants. And so therefore, for infinitesimal q eta, where we recover the actual standard model without the test particle, we get that this square bracket here must vanish. And this is then the condition which gives us the value of delta E over E. So let's write this down. It must be valid for all values of q eta, and for q eta equals 0, we recover the actual standard model, and therefore, in the standard model we have the following result, namely delta E over E plus 1/2 delta ZAA minus sine divided by 2 cosine delta Z ZA equal 0. And that is really the simple result, which is analogous to QED and which corresponds to this more complicated Watt identity discussion that we had the last time. However, the Watt identity was derived at one loop level, and I didn't even show you the derivation, but it is coming on the one hand either from complicated discussions or from explicit one loop calculation. But this discussion here is automatically valid at all orders, and it is anyway much simpler. The resulting form this exact form is not valid at all orders because I did this expansion where the renormalization constants are expanded in first order of the deltas. At higher orders there will be products of deltas on the left hand side, but anyway it's trivial to extend this to all orders. So let me write this. Holds with suitably generalized at all orders. And that was actually a formula which was searched for quite some time. People have derived the two-loop counterpart of this expression when they needed certain two-loop calculations in the electroweak standard model. And those derivations were convoluted and also not really convincing to everybody. But here, with this very simple way, one has found an all-order expression, and now one is sure that also, I mean, the two-loop formulas were correct, but now we have a very simple, elegant, and also powerful derivation. And maybe one can use this idea and the method with this test particle also in other contexts. So it's nice to see that one can do this also in order to study renormalization. Good. This ends our discussion of the on-shell renormalization of the standard model and its interpretation. And now in the last part of the lecture, I would just give you a few minutes of overview of how these loop corrections can be applied in practice and what kind of important loop corrections there actually are, because there are quite some interesting loop effects which play an important role in phenomenology of the electroweak standard model. Do you have first some questions? Questions or comments? No? Okay. Let me clean and then let's go on. Now let's go to explicit loop calculations. And I want to, and we obviously cannot in 1 hour do a lot of different loop calculations, but what I want to focus on are the actual parameters and corrections to them. And this will then, in a way, close the circle to our very first lecture on the electroweak standard model, where we started with simple processes and simple parameters like weak mixing angles defined in the Z interaction, in the W interaction, and so on. And then you get some overview and insight what can happen in general. So let's start with the inputs. So the nice thing about the on-shell renormalization scheme is that it directly gives you an operational definition of all the input parameters. So what are the input parameters? The electron charge, the masses MW, MZ, M Higgs, and then also the fermion masses like the top quark mass and so on. Namely, E is defined as the effective measurable charge measured in low energy interactions with on-shell particles. Effective charge for low energy, which is the so-called Thomson scattering. And the masses MW, Z, Higgs, and M top, and so on, they are defined via the poles of the propagators. There is this subtlety which I mentioned regarding the real and imaginary parts. That was in section 325 such that you do not forget about this. So we were not completely precise in deciding how to treat the subtlety, but there are different ways how to treat it, and one in practice, if you want to be precise, have to decide for one of them and then know the difference. But anyway, if we are at the pole of the propagator, it means that if you look at a process like this, where in an intermediate state there is a particle with all loop corrections applied, then the process and the amplitude behaves like 1 over p square minus m square plus I m gamma, where gamma is the width of the particle, m is the effective mass which is measured, and the whole combination is this complex pole in the complex p square plane. Because as we said, in general, the pole is not on the real axis, but for unstable particles, the pole is in the complex plane and in the negative imaginary part. And but anyway, if you convert this into a probability by squaring such an amplitude, then you simply get a Breit-Wigner peak. And the center of the Breit-Wigner peak is as a function of p square at m square, and the width of the peak is basically given by this gamma here. So, and then of course you have a way experimentally to determine, or let's say maybe square root of p square, then you have an experimental way, and as I said, an operational definition of how to measure the masses and also of how to measure the width of the particles. And that is then converted into the on-shell input parameters. And so let me just for fun give you the numerical values. So alpha e square over 4 pi defined in this way is of course 1 divided by 137 with many, many known digits, which I will not write down. Then the other masses, mz, is 91.1876 with an uncertainty of 21 in the last 2 digits, GeV. So that means the uncertainty is 2 MeV compared to 90 GeV. So this is an uncertainty of much less than 1 per mil. It's a 10 to the minus 4 uncertainty, less than 10 to the minus 4. W mass 80.377 12 GeV, where I took this value yesterday from the particle data group, but as you may know, CDF result is different. So that is the particle data group which compiles regularly the most up-to-date measurements and combines the uncertainties, but they didn't take into account that CDF result, even though that is published, and that differs from this by many standard deviations. So this is one of the problems particle physics is facing right now. But you also see, ignoring that discrepancy, here you also have 12 MeV uncertainty, which is also much better than 1 per mil. Very high precision, but much less precise than for the Z. So the Z has 1 digit more. So the Z is approximately 5 to 10 times more precisely known than the W. And the Higgs, 125.25 with an uncertainty of 17 in the last 2 digits. So this is also 1 per mil. 1 per mil accuracy. And the top quark, 172.69 with an uncertainty quoted of 30 GeV, also from the particle data group. And here the quoted uncertainty is a few percent, few per mil. And so on. But these are the most important parameters for the electroweak physics at the electroweak scale, where, for example, the electron mass is negligible. And then there are quantities like the weak mixing angle, cosine W, CW, which is in the on-shell scheme an abbreviation for MW divided by MC. And we have already given the numerical value of that in the first lecture. Okay, and so you see that actually the input parameters are very precisely defined and very precisely known. Therefore, in the on-shell scheme, we are in a very good position. Our input parameters are basically all known at the per mil level or better. And so that is the starting point for all kinds of calculations. And so we can predict in principle many, many observables with very high precision and therefore test the electroweak standard model very accurately. Now let us discuss the impact of renormalization and sketch then how it comes into play in actual calculations of observables. And we will start with the so-called shift of the fine structure constant. The fine structure constant alpha undergoes effectively a shift delta alpha, which is numerically very large and an important effect in many loop calculations in standard model calculations. Let's see where this comes about. So the on-shell renormalization constant delta E is of course a building block which will enter many calculations, because whenever we do loop calculations we need counter terms, and this counter term will practically everywhere appear. And we have now derived delta E over E is equal to minus 1/2 delta ZAA minus sine divided by 2 cosine delta ZA. So this basically then is determined by the photon self-energy and the mixing. So here photon self-energy, and here fermions can run in the loop like in QED, of course, and for electron and so on it would be the identical Feynman diagram as in QED. But also other charged particles like the W boson can also run in the loop. So here for this delta ZZA, there are actually only non-abelian contributions appearing. Because if the standard model were abelian, then you could prove by using the QED word identity that this must be 0. Therefore, the only non-zero diagrams must somehow know about the non-abelian gauge structure, and those would be diagrams, for example, with W boson loops. So W plus minus, and then you would have here a non-zero Feynman diagram between photon and Z at 0 momentum. And also ghosts could also appear here in the loop. Okay. So then in principle you have to calculate all these loop diagrams, maybe not even only at one loop order, but at all loop orders, in order to get a precise handle on this delta E. Of course there are also ultraviolet divergences in those loops, but in particular there are important finite contributions. And now we focus on one class of finite contributions which enter into delta E over E, which give rise to this numerical shift of the fine structure constant. Namely, a certain class of Feynman diagrams actually have a singularity which makes them particularly large concerning their finite amounts. And these are Feynman diagrams with light fermions. So let us introduce here QED-like notation. So in the standard model we had the notation sigma AA transverse of Q, let's say for a fermion F. And in QED we had the notation pi gamma. And so the relationship is that this sigma AA transverse is the same as Q squared times pi gamma in QED. And for the light fermions at one loop, they behave like in QED, so it makes sense to replace this by the QED building block. So then this contribution of the light fermions at one loop level to this transverse self-energy goes like the QED photon vacuum polarization pi gamma QED with a fermion F, which is a function of Q square. So that is clearly the same. And then we can go to our QED lecture from last semester and copy the results, pi gamma of QED for a fermion F at momentum Q square. So that was quantum field theory 1b, one of the last lectures. Fine structure constant alpha divided by 3 pi times the charge QF square times the following, the divergent term capital delta plus the logarithm of mu square divided by the fermion mass square plus Q square over 5 mf square plus higher orders, where the higher orders are in Q square. So this is an expansion for small momenta. For zero momentum we have just this, and for small momenta we have this linear term in Q square, and then there would be higher order terms in Q square as well. So the point is that this is singular if the light fermion masses go to zero. If a light fermion or any fermion has zero mass, then we get here a logarithm of 0, which is infinite. And if the fermion masses are not 0 but small, then we get here a logarithmic enhancement coming from the small light fermion masses. Therefore, we get here a large contribution, and it is larger the larger the light the smaller the light fermion masses are. And this is an important effect. So let's write this down. This is singular for MF going to 0. It is a so-called mass singularity. And actually, if you look around and look at all loop diagrams which typically appear in Feynman diagrams, then this is the only such singularity for most calculations anyway. If it is the only such singularity, then it means there is precisely this location in our calculation where logarithms of light fermion masses will appear. Those logarithms will be large, and therefore we can control the large light fermion logs by just focusing on this contribution here. And then we know for most calculations where this statement applies, there are no other singularities in the fermion masses. Then we immediately can, let's say, take into account the large logs from light fermions by only looking at the contribution coming here via the renormalization constant delta E. And for this reason, one defines now a shift in the fine structure constant, which is the following. Delta alpha, a shift in alpha, is defined as follows, namely, we take just a logarithmic term, basically, pi gamma coming from light fermions in QED or in the standard model AA at 0 minus pi gamma from the light fermions AA at a different momentum, namely at mz square. You could do it also for other momenta, but typically one chooses the z mass square. In general, one could also have delta alpha at q square, and then you put over there some q square argument. Okay, but that is the most common thing. And if you do that difference, the difference means that the divergent delta drops out in the difference, so this delta alpha quantity is finite, and the large logarithms, they remain. So, and we didn't evaluate exactly that, but let me give you the result. The result of the difference is alpha over 3 pi times the sum over the light fermions, and for each light fermion you get qf square times ln mz square divided by the light fermion mass square minus 5/3, some constant additional term also. And so the logarithm of the unphysical scale mu also drops out in the difference, and so you get here a physical large logarithm between the Z mass and all the light fermion masses. And so in particular the electron will give a large contribution here because it's 10⁻⁴ times smaller than the Z mass. So this is a large contribution. So, and okay, so let me say it actually here. So this delta alpha gets the following numerical value. You can split it into delta alpha from leptons plus delta alpha from hadrons, and this is around 3% plus 3%. So both shifts from both delta alphas are around 3%, and so in total this delta alpha shift is 6%. So it's quite a large shift, and if you remember that all the quantities are measured to 10⁻⁴, then 6% is an incredibly large dramatic effect, which of course must be controlled and taken into account in calculations. So now the question is, how does this actually appear in calculations where you do not just calculate delta E, but you calculate an observable quantity? Where does this come into play? It comes into play in the following way. Typically, calculations of physical quantities will be proportional to some power of the charge, for example, E square at lowest order. Then, at higher orders, when you do loop calculations and renormalization, the E square will be replaced by E square plus 2 times delta E over E because of the renormalization transformation. And so then, including higher orders, your calculation will involve a factor E square over 4 pi times this correction here. And this correction is now delta alpha. So this is equal to alpha times 1 plus essentially this pi gamma, pi AA at 0, because this delta E over E is to a good approximation for the light fermions. We can ignore this delta ZZA because that doesn't contain fermions, only this contains fermions. This comes from the QED pi gamma. So that is what we have, and this pi gamma AA gives exactly the 2 times delta E over E. And now we can replace this by alpha times 1 plus pi AA contains divergences, and it contains the large logs, and it contains the unphysical scale mu square. So this can be written as follows. It can be written as delta alpha plus a rest, namely pi AA rest, let's say, at 0 minus pi of the light fermions AA at mc square. Okay, so I have simply extracted pi AA. I write it as pi AA from the light fermions plus pi AA from the rest, and then I add and subtract the light fermions at mz square. And in this way I have artificially introduced the quantity delta alpha, and here is the remainder. So there is additional diagrams at 0 momentum, and we need to again subtract this pi here. Plus, then the sign is correct. Okay, so now why that split? This delta alpha is now finite. It doesn't contain ultraviolet divergences, and it doesn't contain the unphysical renormalization scale mu. However, it contains physical large logarithms of the light fermion masses, which is an important effect. Those remaining quantities at 0 momentum do not contain singularity, so they are small. And those additional Feynman diagrams, or the light fermions at the Z mass scale, they also do not contain singularities because there is the Z mass scale which prevents such a low mass singularity. So this is regular for light fermions going to 0. This is regular for light fermions going to 0. Therefore, we can simply say this is not singular, and therefore it is not enhanced. And so we can simply say at this point it is small. It is small because it is not enhanced by the light fermion masses. And what it is exactly, we don't know at this point, but it is something which does not have this interesting enhancement from the looks. Therefore, we can say in an actual calculation, which at tree level contains the fine structure constant alpha, what will happen at higher orders is that inevitably this alpha will be replaced by alpha times 1 plus delta alpha plus small corrections. And this delta alpha is the single source of singular logarithms of the light fermions. So, renormalization amounts to this replacement delta alpha summarizes the singular ln m fermion terms. So therefore, you can now see that in essentially all electroweak loop calculations, this will appear. And the discussion that you might have and that you should wonder about, maybe offline or now, renormalization amounts to this replacement delta alpha summarizes the singular ln m fermion terms. So therefore, you can now see that in essentially all electroweak loop calculations, this will appear. And the discussion that you might have and that you should wonder about, maybe offline or now, is why does this not play an important role also in QED, where we didn't discuss it like this? Why is it particularly important in the standard model? And that has in one way to do with my statement that in most calculations this is the only source of such a mass singularity. Maybe in some calculations that is not true, and then of course this replacement doesn't make sense and it will not give an important or relevant contribution to the final result. Only in those calculations where indeed this is the only singularity for light fermion masses, this is a quantity which is worthwhile isolating. And the point is that the electroweak calculations typically happen at a physical energy scale around the Z mass or W mass, which is a very high energy scale, much higher than the light fermion masses. And because of that, these logarithms are very large. And in QED, you typically consider processes which do not happen at very high scales, but maybe at the electron mass scale, and then the log of the energy divided by the electron mass is not enhanced, and there is no way, physically speaking, to assume that the electron mass is infinitesimally small compared to the energy scale of relevance for your process, because you're looking at electron scattering at electron energies. So therefore, only at electroweak physics, where the energy scale set by the electroweak bosons is very high, this is a relevant effect. And if you look at other physics situations, maybe at intermediate energies or at even higher energies than electroweak ones, then this discussion should be modified appropriately. But for
طبعا هذا يتفق مع نظريتي أنه كلما دخلنا عمقا كلما زادت ألفا، كلما زادت ألفا، لأنه كيو دي كما ذكر أن الريليشن في اللوغاريتم يكون الإلكترون إلكترون مثلا أو بالنسبة للإلكترون، لكن في الإلكترويك يكون relative to بوزون، وهي طبعا أعلى قليلا، أعلى من الإلكترون، وبالتالي نجد أن ألفا تزيد. زيادة ألفا ناتج من زيادة الطاقة، هذا واضح جدا. زيادة ألفا ناتج من زيادة الطاقة، وبالتالي تتحول ألفا إلى جي كيو سي دي التي تعتبر 1 من 10⁻⁴ إلى 1، وربما تزيد في ذلك. وهذا ينعكس عن النسبة بين المجال، النسبة بين الكهرومغناطيسية والجاذبية. هذه النسبة الضخمة 10⁻39 ربما تنقص قليلا، لأن الجاذبية تلعب دورا أيضا، برغم أن الفضاء ثنائي الأبعاد يحاربها، لكن في النهاية هي مسؤولة من التفاعلات بالمناسبة، ليست الكهرومغناطيسية. الكهرومغناطيسية مسؤولة من الروابط، لكن الجاذبية والكتلة هي مسؤولة من التفاعلات، حيث أنه إذا زادت الطاقة هذا يعني زاد الكيرفيتشر، والتأثير الأكبر للكيرفيتشر ناتج من الكتلة، لأن الكتلة ضخمة، وبالتالي تزيد التفاعلات حدة مع زيادة الطاقة، فإن الجاذبية هي مسؤولة من التفاعلات. وهذا ما جعل كيو سي دي تختلف عن باقي القوة، بحيث أن لها أبعاد مختلفة وديجريز اوف فريدم مختلفة، لأنه ما يؤثر في التفاعل هو الجاذبية، ولهذا هم يعبرون عن ذلك بهذه الأبعاد المختلفة، وهي طبعا أكبر من الأبعاد الرباعية، حيث أن الفيرميون لديه 3 أبعاد والجلوس لديه 8 أبعاد، هكذا يعني 8 degrees of freedom للفوتون للإلكترون للفيرميون، و 8 degrees of freedom بالنسبة للجلونز. فهذا ناتج من هذا النوع من التفاعلات.
processes which really happen at the electroweak scale, this is typically a very important and effect and a useful thing to think about. And so in the on-shell renormalization scheme, that fine structure shift enters via the renormalization constant of the electric charge. And as some of you might know, there are renormalization group techniques and the MS bar renormalization scheme, where one can also define a running coupling constant, and then essentially the same effect is taken into account by the running of the coupling constant, which then runs to high energy scale and resums those large logarithms. But this is not the same mechanism, but it is related and gives rise to the same kind of logarithms, but in a different technical way. Yep. Typically to the highest energy scale of relevance for your process. So yes, so in case we do scattering of W bosons, then this would be the energy scale. If we calculate decay of the set or decay of the Higgs boson, then that would set the energy scale up to which we integrate the renormalization group equations. In the context of, yeah, okay, other question?
The small remainder, does it now contain the UV divergences?
Yes.
Okay.
Yes, and they of course cancel against other stuff in the full calculation. clearly we know that the ultraviolet divergences cancel, and so they are neither large nor small, they cancel anyway, and we are caring here about the additional finite pieces which enter the renormalization constants. And this is an important large finite piece. Maybe the logic of what I'm doing here is I want to make you aware, most of all, that these quantities and these parameter shifts exist, and whether they are important for your calculation that you do in your daily life, you have to figure out yourself. But typically I am saying these quantities are important, and that is why I want you to know about them and their interpretation and their sizes and their origins. There is one second quantity that I want to discuss in the same way, and then we come to the muon decay as an example. And the second quantity is the rho parameter. So let me remind you of this miracle in the standard model. One of the many miracles was the so-called rho parameter, which is equal to 1. The so-called three-level rho parameter, which was defined to be mw square divided by mz square times the weak mixing angle cosine square. And this at 3 level is exactly equal to 1. That was a miracle in the sense that it relied on this custodial symmetry, a hidden symmetry which was not part of the invention of the standard model, but which nevertheless exists in it, and which guarantees that the mass matrix contains 3 equal entries instead of 2, which would be the general consequence of SU2 cross U1 broken down to SU2U1. So the 3-level rho parameter in the standard model is 1 because we break the SU2 cross U1 symmetry by a Higgs doublet instead of something more complicated like a Higgs triplet. And experimentally, this ratio also is approximately 1, but it is not exactly equal to 1. And we already saw that the custodial symmetry which backs this up is actually violated. It is not an exact symmetry of the standard model, but it is violated by higher order corrections coming from the top quark, and so this relationship will be modified by loop corrections. And the shift in the rho parameter, called delta rho, is coming from these important loop corrections which break custodial symmetry and which give rise to differences here which are actually observable and which are observed. So this is a second very important such parameter shift, which again enters many calculations in a kind of universal way. So in the on-shell scheme, let's first of all remind ourselves that there is no variable for the weak mixing angle. So in the on-shell scheme, there is only the variable CW and SW, which by definition is exactly equal to the mass ratio. So in the on-shell scheme, we cannot really speak of corrections to this equation. It doesn't make sense. So this is exactly true by definition. But there is an important renormalization constant, namely, an interesting renormalization constant would now be delta of the weak mixing angle square, delta CW square. This will for sure appear in calculations, but as I already told you, this is to be regarded as an abbreviation for the renormalization of that. But anyway, even in this way, this renormalization constant is important and it will appear in calculations. And what is that actually? This is evaluated as a differential, so this is delta mw square divided by mw square minus delta mz square divided by mz square. So this is the renormalization of the weak mixing angle. And so actually, I forgot to divide by cosine square on the left-hand side. And delta cosine square is the same as minus delta sine square, so this is also equal to minus delta SW square divided by cosine W square. Okay, so don't get confused. I have here delta sine square divided by cosine square, because the sum delta sine square plus delta cosine square is 0. Because sine square plus cosine square is always equal to 1. So these are important building blocks, and for sure they will appear in some calculations. Now let us define a building block which is delta rho, namely delta rho.
طبعا في هذه الآلية أنا ذكرت أن كلما زادت الطاقة كلما تقاربت كتلة الويك كتلة الزي من كتلة الويك، يعني زي أصبح أكثر عمقا في الانتقالات المجالية الكهربائية إلى الانتقالات المغناطيسية. إذن كتلة الدبليو الهيجز ستنقص، وبالتالي نجد أن الكوساين ينتقل من 0 إلى 1. هذا ما ذكرته. إذا حصل ذلك فهذا صحيح، وإذا لم يحصل ذلك، إذا حصل العكس، يعني الكوساين هذه اللي هو الويك ميكسينج أنجل، إذا لم تزيد من 0 مع زيادة الطاقة أو الزيادة الدلتا مفترض أنها تكون زيادة على الزاوية، لأن الزاوية مفترض تنتقل من 0 إلى 1 أو من الأقل إلى الأعلى، وهذا يعطينا أقصد من تنقص من الأعلى إلى أسفل، لأن الكوساين ينتقل من الأسفل إلى الأعلى من 0 إلى 1. هنا نجد أن الساين على الكوساين أو الدلتا ساين على الكوساين، الساين مفترض أن ينقص والكوساين يزيد هكذا. إذا الدلتا مفترض تكون ناقص، يعني بينها علامة ناقص. المهم إذا كانت الإجابة صحيحة، إذا كانت طابقت ما قلته في Renormalization، فهذا يعني الدبليو الذي تقترب من الدبليو عند الطاقة العالية. إذا كان الإجابة خاطئة أو العكس تماما، فإن الدبليو تقترب من الزي، وهذا يعني أنا لدي مفترض أن أفسرها تفسير آخر. يعني إذا أتحدث عن زيادة الطاقة اللي هو UV divergent، مفترض إنه الزي تقترب من الدبليو عند الطاقات العالية، مفترض الزي تقترب من الدبليو، بالتالي كتلة الزي تقترب من كتلة الدبليو. لنكتشف ذلك.
Is defined at least at the one loop level as the following: sigma zz at 0 transverse divided by mz square minus sigma ww transverse at 0 divided by mw square. This is the definition of the so-called delta rho parameter, and it is obviously related to the renormalization constants that you see here, because delta mw and delta mz are determined in terms of those self-energies. Only one should calculate them with self-energies on shell instead of at 0 momentum. But you see in this way that delta rho is kind of an approximation to this expression. It's an approximation for this expression evaluated at 0 momentum. So, and therefore you can say the following important contributions are as follows. So delta CW square divided by CW square is now the following. So here sigma ZZ is essentially delta MZ square, so this is the negative of this. So this is approximately equal to delta rho plus small corrections. Okay, we don't know for sure that they are small, but let's say it's essentially minus delta rho plus some additional terms. Similarly, delta SW square divided by SW square, so the relative correction of the sign, is then given by this multiplied with the appropriate mixing angles. So that would be plus CW square divided by SW square times delta rho plus dot dot dot. Okay, so here I get the minus and the product of the two mixing angles in this ratio. So CW square is bigger than SW square, so that is an enhancement here. And what is particularly interesting, delta, let's say E divided by SW. Who remembers what is this ratio, E divided by SW? What is its meaning and its role? Where does it come from? From the beginning stages.
الدلتا بإشارة ماينس ليه؟ الدلتا رو بإشارة ماينس، هذا يعني أن الدلتا رو تنقص من رو، وهذا يعني أن الكوساين ينقص. الكوساين يزيد، نعم، الكوساين يزيد. الرو إذا نقصت يعني المقام يزيد، يعني كتلة الدبليو، كتلة الزد تزيد على الدبليو. إذا نقصت رو فهذا يعني كتلة الدبليو تزيد على الرو، زي كتلة كتلة أقصد كتلة إذا زادت رو تعتبر كتلة الزد تنقص، إذا نقصت رو تعتبر كتلة الزد تزيد، وإذا كتلة الزد نقصت فهذا يتفق مع نظريتي، وإذا زادت هذا يعني أنا أحتاج إلى تفسير آخر أو تعديل، أو ربما فقط نسيت بعض الأشياء هذه الأشياء التي نسيتها يعني تحتاج إلى تعديل.
Of the standard model theory, where we introduced the weak mixing angle. So that is the
We calculated the kinetic term of the X field, and there we had these corrections, the coupling strength.
That is right. So it generally appears in the covariant derivatives once we express them in terms of photon Z and so on. And why does it do that? Because that is actually nothing but the gauge coupling GW. The gauge coupling GW was eliminated in terms of the weak mixing angle and the electron charge, and so that is exactly the GW. And so, of course, in some processes, some Feynman diagrams effectively GW will appear, but we are not allowed to use GW. We must express everything in terms of our fundamental parameters, but nevertheless, this is still an important building block. For example, the W boson interactions go just with GW. So the W interactions will, in the on-shell formalism, always have this ratio here. So therefore, what is the counter term for this ratio? And even diagrams typically contain 2 powers of the coupling, so let's immediately do it with 2 powers of the coupling. Then what happens here in this case? So in this case, we get E square times SW square as a prefactor, and then we get a relative correction. The relative correction to this is 2 times delta E over E. But what is 2 times delta E over E? 2 times delta E over E is approximately delta alpha. So we get here delta alpha plus some smaller corrections. Then we get minus delta SW square divided by SW square, so we get minus this.
ربما يكون التفسير كالآتي: أن زي ثابتة، كتلة الزي بوزون ثابتة، بالتالي كلما اتجهنا عمقا التفاعل الزي لا تقترب من الدبليو، لكن الدبليو تبتعد من الزي أكثر لأن الدبليو تنقص. الزي ربما يكون لديها خصائص أنها تقف فقط في حدود المجال الكهربائي والشحنة بين المصفوفة، والدبليو هي التي تزيد. يعني هناك أكثر من تفسير لهذا، يمكن العلماء أن يبحثوا في هذا الأمر.
Minus CW square over SW square times delta rho, and then plus some maybe smaller corrections. So this is how this appears. And so now you see that when you have some process with couplings involving this GW, then inevitably when you do one loop calculations, there will be counter terms, and those counter terms will inevitably contain this combination. So there will be a large effect, 6% from delta alpha. You cannot avoid it. And there will be a large effect coming from delta rho. You cannot avoid it. What we don't know is whether the additional terms are maybe even more percent or whether they are small. That depends on the case, but for sure those corrections exist. And so therefore now we should focus on this delta rho and explain what it actually is. So the point is that there are large loop corrections to this delta rho. And they are connected to the breaking of custodial symmetry. So should we check this? It seems okay. Here as well. Large loop corrections from top and bottom. So as I told you, the custodial symmetry were exact if the top and bottom Yukawa couplings were equal, because then we could write the entire Yukawa Lagrangian in terms of this 2x2 matrix valued Higgs boson field with a universal up-down Yukawa coupling. But they are obviously not equal. They are very, very different, and not only different, but one of them is really absolutely large. And therefore, there is a strong breaking, but of course that breaking affects only one loop corrections and is not present or not visible at tree level. And this violates custodial symmetry. And therefore we get large corrections. And the basically order parameter of this violation is the difference between the two masses, so those corrections will be somehow proportional to the difference of the masses. And let me just give you the result. What you need to calculate is this W boson self-energy with a top and bottom loop here mixed, and you also need the Z boson self-energy with either top quark or bottom loop. And then once you did everything, you can compute the self-energies at 0 momentum, plug it into the relationship, and then you obtain the following. Namely, I think that might just fit here, delta rho from top bottom is equal to the color factor NC, which is 3, times alpha divided by 16 pi SW square CW square times the Z mass square times maybe it doesn't fit. Okay, let me make it fit. Times the following: m top square plus m bottom square minus 2 m top square m bottom square times ln m top square divided by m bottom square and divided by the difference m top square minus m bottom square. Can you read this? So this is it. So this is not singular if the masses are equal. If the masses are equal, the denominator goes to 0 and the numerator also goes to 0 because we get log of 1. And so the ratio between numerator and denominator goes also to 1. And then for equal masses, that drops out and we simply have 2 times mass square minus 2 times mass square is 0. So therefore, at equal masses, that correction vanishes, which corresponds and reflects custodial symmetry. But if the masses are not equal, that obviously does not vanish. And if in the real case where the bottom mass actually is negligible compared to the top mass, let's say just a square bracket, you can write down the whole thing, but the square bracket simply converges to the top mass square. And then simply you can replace the entire square bracket by m top square. And what you see is that the final result for this delta rho top bottom behaves like alpha times m top square divided by mz square. And that is a large correction because the top mass is very large, larger than the z mass, and therefore we have here also a significant effect which is enhanced. So, and how large is it actually? So alpha is around 1%, as you know. This is bigger than 1%. There are some other prefactors involved and also a color factor of 3. So ultimately, this delta rho from the top bottom sector is around 1%. It's a 1% effect, which is significant also again in the context of these per mil precisions for the input parameters. And if you look at this formula here, then very frequently this combination will appear, and in this combination the rho parameter is enhanced by a factor 3 to 4. So then this would be a 6% and that a minus 3% effect. Two very important effects which we have now isolated and which have two very well-defined origins and which appear universally in many electroweak calculations. Okay, so that ends our discussion of the rho parameter, and now
دلتا، هنا دلتا عندنا دلتا كوساين سكوير للدبليو على كوساين دبليو على كوساين سكوير دبليو، دي يساوي ناقص ساين على كوساين. طيب هنا جبنا ايه؟ هنا ناقص كوساين على الساين، يعني معكوس هذه المعادلة، ناقص كوساين على الساين في الدلتا، دلتا رو، وجاءتنا الدلتا رو عالية، إذا دلتا ألف نقصت. هنا دلتا ساين على ساين أوميجا، دلتا كوساين هذه هي دلتا كوساين على ساين يساوي ناقص دلتا رو، والناقص دلتا رو جات عالية، دلتا رو عالية بسبب الاختلاف بين كتلة الطب وكتلة البوتوم. هنا ماذا تؤثر على هذه المعادلة؟ كوساين على ساين هي عالية، وبالتالي الدلتا على الكوساين عالية، هذه يعني أن زادت الدلتا كوساين تربيع على ساين، هذه يعني زيادة الدلتا كوساين على كوساين، هذه المعادلة، زيادة هذه المعادلة تؤدي إلى زيادة الفرق بين طيب هنا كوساين زادت، دلتا كوساين دبليو على دلتا دبليو، نعم هنا زادت، هنا زادت، هذا يعني أن هذه الدلتا أيضا تزيد، يعني الفرق بين الكتلة الزد وكتلة الام تزيد، كتلة الدبليو وكتلة الزد تزيد، الفرق بينهما، وهذا يعني أن كتلة الدبليو وكتلة الزد تكون ثابتة بأي طريقة ما، هي ثابتة، اللي هي تعبر عن الدمج بين التي 3 والواي تعبر عن التي 3 والواي تعبر عن المجالات، الاحتمالات المجالات الكهربائية على الاشتقاقات الزمنية، هذه تظل ثابتة، وهذا يدل على أنه القياسات كلها تعطينا كتلة الزد ثابتة، لكن كتلة الدبليو غير ثابتة، تعتمد على الطاقة، فبالتالي نجد أن الزد لا تدخل مع زيادة الطاقة، لا تدخل في لا تتحرك من الريجون، اعتمادات المجال الكهربائي على الاشتقاقات الزمنية، إلى اعتمادات المجال الكهربائي على الاشتقاقات المكانية، أو يصبح مجال مغناطيسي، وإنما تزيد الهوة، نعم تزيد الهوة بين المجال الكهربائي والمجال المغناطيسي. هذه أيضا تفسر نظريتي بالمناسبة، كما ذكرت أنه ربما يكون أشياء فاتتني ويكون نظريتي صحيحة، ويكون هناك أشياء فاتتني. زيادة الطاقة تؤدي إلى زيادة الجنريشنز، الطاقة الكتلة بين الجنريشنز، وهذا يؤدي إلى زيادة الفرق بين المجال الكهربائي والمجال المغناطيسي، كأنما الطاقة الكلية تساوي طاقة الوضع زائد طاقة الحركة، طاقة الحركة هنا بالسالب، وأعتقد أنه طاقة الوضع تظل ثابتة، لكن طاقة الحركة هي التي تزيد بناء على حساب طاقة الوضع، أو طاقة الوضع ثابتة، طاقة الحركة تزيد، وبالتالي نجد أن الطاقة الكلية المفترض تكون ثابتة، فطاقة الوضع تنقص، لكن هنا لا يحصل ذلك، هنا يحصل أنه طاقة الوضع ثابتة وطاقة الحركة تزيد، وهي بإشارة السالب، وبالتالي تنقص طاقة الوضع وتكون الطاقة الكلية هي ناقصة ليست ثابتة، فهذا كثر من التناظر، والإعادة في ذلك إعادة كثر التناظر، من أجل استعادة كثر التناظر هو أن نجعل كتلة ال W تنقص، حتى زيادة طاقة ال W ونقصان كتلة ال W تتساوى مع حفظ الطاقة الكلية. الطاقة الكلية هنا تمثل ماذا؟ تمثل الطاقة التي جاء بها الفوتون أو طاقة التصادم. طاقة التصادم كلها ثابتة، تحتمل هي طبعا ليس ثابت، تحتمل على مسافات التصادم، المسافات التي تحصل فيها التصادم، وبالتالي نجد أن كل مساورة المسافات هذه يؤدي إلى زيادة الفرق بين الجنريشنز، وهذا ناتج من هذه الآلية. إذا نظريته صحيحة، لكن تحتاج إلى تنسيق أكبر، إلى يعني فهم أعمق. فالأمر ليس بالضبط مثل طاقة الحركة زي طاقة الوضع، لا، من الأمر يختلف كثيرا، لأنه نحن نتكلم عن كثرة التناظر. هذا كثرة التناظر متغير بالنسبة للصراع بين الفضاء الصناعي بعد الكتلة. أما على سطح الأرض فنجد أن التناظر ثابت، اللي هو الطاقة الكلية ثابتة، وطاقة الحركة زي طاقة الوضع، كلما زادت طاقة الحركة نقصت طاقة الوضع. هناك لا، لأن هناك صراع بين الفضاء الصناعي بعد والكتلة، فإن الطاقة الكلية أيضا ليست ثابتة. ترجع هذه الطاقة الكلية بعد تغلب الفضاء الصناعي بعد على هذا الصراع، تفريغ الطاقة، ترجع الطاقة الكلية وترجع سيمتري مثل ما كان، اللي هو في الأونشيال عندما بي تربيع يساوي تربيع.
If we have time, okay, whoever wants to leave or has to leave is obviously allowed to leave, and who needs a shine can get a shine. But otherwise I will continue, because it would be a pity to stop now without having introduced one of the most important actual loop calculations in the electroweak standard model, namely the muon decay. And in the case of muon decay, we will actually see all these effects come into play, and it is tremendously important for testing the electroweak standard model, both historically but also.
طبعا الميون ديكي، الميون يحصل له ديكي حسب نوع الميون، إلكترون ونيوترينو، أو بوزيترون أنتي نيوترينو، أو فوتون. الفوتون قادم من الميون نوت، وهي ميون نوت قادمة من الزي، الديكي للزي أيضا يعطينا ميون نوت، 2 ميون نوت على ما أظن. الدبل أيضا يعطينا ميون نوت عند الطاقات العالية بالمناسبة، زائد ميون موجب على ما أعتقد، زائد نيوترينو. هذا الدبل الزائد والدبل الناقص أيضا. فعند الطاقات العليا يعطينا ميون، عند الطاقات الدنيا يعطينا إلكترون ونيوترينو. فنتأكد من هذا الأمر، هل هو عند الطاقات العليا يعطينا الميون حتى تزيد الفرق بين الكتل، الطاقات العليا، عند الطاقات العليا تنقص الفرق بين الكتل. وأيضا نجد أن الزي عند الطاقات العليا، الزي مفترض أن ينتقل من الفوتون إلى أنه يعطينا ميون نوت. طيب تعالوا نشوف هذا الكلام.
Presently, because there is a controversy associated with the measurements, and so therefore this is something which is worthwhile knowing, and so let me just introduce it a little bit to you. Do you have any other questions? Should we make a break? No. Okay. Good. So let us go on and do an example for radiative corrections. Muon decay. And as I said, we close the circle to our very first lecture, where we already wrote down the muon decay. So it looks like this. Muon decays into muon neutrino, anti-electron neutrino, and electron. And up to certain well-defined prefactors, the entire amplitude defines the muon decay constant G mu.
نسيت أنه يعطيني اثنين نيوترينو وليس واحد نيوترينو، نسيت هذا. فأيضا تنطبق النظرية أيضا، ليست هناك مشكلة في الفروقات بين الكتل، بس لاحظ الفروقات بين الكتل مع زيادة الطاقة تزيد، مع نقصان الطاقة تنقص.
When we calculate the muon decay at 3 level, then the Feynman diagram is this one. We have a W boson in the intermediate state. The initial and final states are what I wrote before. And this 3-level Feynman diagram gives rise to a value of the muon decay constant G mu, which is as follows. We have to read off from the diagram. E square divided by 4 square root of 2 mw square times SW square. Okay. What that means is that you calculate the Feynman diagram, and then by definition you apply certain prefactors which are defined also for the experimentalists. So this is a universal definition which I do not have to repeat here. But the experimentalists know how to convert their measurement into G mu, and the theorists know how to convert the Feynman diagram into G mu, and then the standard model prediction is this. So this is essentially the coupling constants from the two vertices and 1 over mw square from the propagator. And here you see appearing our famous and beloved E square over SW square, which comes from the gauge coupling GW sitting at the two vertices. And the 1 over mw square comes from the propagator. So remember that the momentum which flows through the line here is totally negligible because it has the energy scale of the muon mass compared to the W mass. Here it's negligible, and therefore we just approximate the propagator by 1 over mw square. So that is the 3-level result. And the exact result in the on-shell scheme is as follows. So we cannot do the calculation, but we have a definition. The exact result is the same formula times 1 plus delta R, and then delta R by definition summarizes all higher order corrections coming from standard model theory in the on-shell renormalization scheme. So this effectively defines a quantity delta R, which is somehow small. Now what we want to do is to get a hold on this delta R. So in other words, we want to compute the one loop correction to muon decay in the standard model. And in other words, we want to compute the one loop correction to delta R in terms of an approximation, as good as we can in 20 minutes. And then the way it is used in reality is the theory predicts a certain value of delta R, which is, let's say, still a function of standard model parameters like the top quark mass, bottom quark mass, Higgs boson mass, and so on. Or let's say a percentage, maybe 2%. And then you would know, okay, if I measure the muon lifetime, and I know about these 2%, and I know the Z boson mass which goes here, then I can calculate the W mass from inverting the relationship. Or I can test the standard model validity by plugging in all the measured values into all the quantities and check whether it agrees with the calculated value of delta R. Or you say, I know all the quantities like MW, MZ, muon decay, electron charge, and within here I know everything except for the top mass, but the top mass enters delta R, and so therefore I can solve comparing theory and experiment and get a prediction for the top quark mass. Or I can predict the Higgs boson mass because the Higgs mass also enters delta R. So these are all possible ways in which you can use this relationship. it's a standard model prediction for the correlation between observables, and you can solve it for any observable that you want. Currently, it is mainly used for predicting the W boson mass, because this is the crucial quantity which is least precisely measured compared to the, let's say, precision that we can achieve in the calculation. Let us do the calculation. One loop in one shell scheme. So what are the Feynman diagrams which appear in a one loop calculation? So there is the following Feynman diagram. This sort of thing, where we have all sorts of one loop diagrams in the W boson propagator. That gives the W self-energy. There are all sorts of Feynman diagrams of this kind, where we have a vertex correction in this vertex, similarly in the other vertex. And there are so-called box diagrams. And there are counter term diagrams, let's say plus. This counter term diagram. This counter term diagram. And this counter term diagram. These are precisely the only three counter terms diagrams which exist for the calculation, but there are of course many loop Feynman diagrams which appear. But this is the full structure of the one loop calculation. So just as some examples, or do you need examples? Example?
Just a question, how would you do the box diagrams in this notation? Would you just do the box and then just write?
Yeah, well, that's why I wrote it as a word, because it becomes a little bit, yeah, I mean, of course, you should write it like this, but this seems to me a little bit ambiguous, because we already used that same symbol for the full process. And so, but box diagrams are one particle irreducible diagrams of this structure. Okay, so that's it. Now, one thing that is important for the calculation is that here the momentum q square in the propagator is much, much smaller than mw square, and so we neglect the momentum and set q square to 0, such that the W boson propagator just becomes 1 over mw square. Good. Then let's evaluate all the diagrams to the approximation that we can manage immediately. So before I delete it, it is clear that our muon decay contains exactly that ratio which I have announced, and therefore it will contain exactly that combination. So you can already memorize this. I first wanted to look at the diagram with the W boson self-energy, and there I would look at the counter term and the self-energy simultaneously. So let's call it diagram 1 plus 6, the first and the last diagram together. They involve the following combination. Here the loop plus the counter term, and both appears inside of the propagator. So for the diagram, we essentially only need the transverse part. The longitudinal part drops out of the diagram because of the external lines, and then we obtain for the transverse part here minus I divided by minus mw square, because we neglect the q square in the denominator, so we have this simple term from the left. Then in the middle we have minus I times sigma ww at 0 momentum, and here we have plus I times delta MW square minus I times delta ZW times MW square times another minus I divided by minus MW square. Okay, so this delta MW square and delta ZW, that comes from the renormalization transformation and the counter term. So the mass counter term is obvious, I hope, and the counter term delta Z multiplies normally P square minus M square, but P square is 0, therefore here it only multiplies minus M square. So, okay, good. So what is this in total? It is plus I divided by MW square times which correction? So which correction? So this minus I divided by minus MW square times this gives plus sigma WW at 0 minus delta MW square, and the whole thing is divided by MW square. This comes from those two objects. And then we get an additional minus I times plus I plus delta ZW times 1, and the rest has cancelled. So this is the tree-level propagator from the tree-level Feynman diagram. And that is a correction. So the diagrams 1 plus 6 together, they are equal to the tree-level Feynman diagram times the round bracket. That's exactly the effect. Everything is tree-level and it is multiplied by this exact bracket. Self-energy and the two renormalization constants. Now, what about the diagrams with a counter term here at the vertices? Let's call it diagram, what is it, 4 and 5. In the diagrams 4 and 5, what we get is the W boson counter term to two fermions. What is the value of the W boson counter term to two fermions? It is equal to the tree-level vertex of the W to the same fermions times the renormalization constant. But what is actually the renormalization constant? You always get it in the same sort of way. The coupling gets renormalized, and the coupling is here the coupling of delta E over SW, our famous combination, because that originates from GW. Then divided by the tree-level term. And but then we get additionally field renormalization plus 1/2 delta ZW. Actually, question, did I make here a sign mistake? So in the self-energy of the W boson, we definitely get, yes, of course there is a sign mistake, because minus I delta Z is multiplied with P square minus M square. P square is 0, but minus M square. So we have this, and then we have here minus. Okay, good. Sorry about this. Anyway, then let's go on. Here plus 1/2 delta Z for the W boson field renormalization, and then we have some 1/2 delta Z for the muon, and 1/2 delta Z for the neutrino, depending on which fermion we are looking at, muon or electron neutrino. All right. Therefore, all the diagrams that we have so far looked at, diagram 1 plus 6 plus 4 plus 5, they all have a simple feature, namely they are proportional to tree level, and between them the field renormalization of the inner line, the W, cancels. That is a typical feature. So look at this, please. So here the delta ZW enters as follows. We get tree level times minus delta ZW. Here we get tree level times plus 1/2 delta ZW, and that appears twice, once from here and once from here. So overall we get tree level times minus delta ZW plus 2 times 1/2 delta ZW, so delta ZW cancels. And that is always the case if you have field renormalization for internal lines. It always drops out between the counter terms for the propagator and for the associated vertices. And it just tells you again that field renormalization is unphysical. It doesn't depend how you normalize your fields. The Feynman diagrams, and in particular S matrix elements, do not depend on this. So it has cancelled, and what remains is proportional to tree level. So therefore the sum of those 4 diagrams is equal to the tree level diagram times the following correction, namely sigma WW at 0 minus the renormalization constant delta MW square divided by MW square. Then here the counter term that comes also twice, 2 times delta E over SW divided by E over SW, so the relative correction, plus fermion field renormalization. So delta Z for the 4 fermions. Now what happens to those quantities, and what are the dominant terms? So the most important terms in all the Feynman diagrams are the following. So first of all, so far we didn't talk about the box diagrams and those vertex corrections. We ignored them. And that is because we do not know any potentially interesting effect which would make those diagrams particularly large. Therefore, we ignore them. We assume they are small. And in those corrections that we have looked at, diagrams 1, 6, 4, 5, we have this part coming from the self-energy and the counter term. We have this part which we have already analyzed, and there we get delta alpha and delta rho. And we have the fermion field renormalization. Now, of course, you might have to calculate to check it all, but it's indeed the case that the fermion field renormalization doesn't give large effects, neither enhanced by logarithms, nor enhanced by m top square in the numerator, nor by anything else. Similarly, the box diagrams and vertex corrections, they are not enhanced by anything particular. Therefore, they are indeed small, but inside of here there are 2 effects which have special enhancement mechanisms. And then what remains is this one here. That is essentially 0 because that is given by the on-shell self-energy. So the difference just comes from the momentum dependence of the self-energy, which is also not enhanced by anything. So in other words, the dominant terms are just from delta E over SW, which provides delta alpha and delta rho. And let me just say, sigma WW of 0 minus delta MW square is nothing but sigma WW of 0 minus sigma WW of MW square, which is assumed to be small. Fermion field renormalization is small. Vertex box diagrams are small, and therefore everything is small except for our renormalization constant. And so now you see an example of a loop calculation where actually, lo and behold, everything boils down to calculating renormalization constants. So the actual one loop Feynman diagrams for muon decay have dropped out. The only diagrams that you need to calculate are the ones which go into the renormalization constant delta E and delta SW. So it's a neat effect and shows off the importance of renormalization. So overall, the one loop correction to muon decay is given by tree level times 2 times delta E over SW divided by E over SW plus small terms. And since we have conveniently already evaluated this, we get tree level times delta alpha minus cosine W square over sine W square times delta rho plus small corrections. And in general, our loop corrections are summarized in the quantity delta R. So now we can bring it into a form for this delta R. What we have done is calculate all the loop corrections, and we interpret now the result in terms of G mu or delta R. And so it's exactly defined in this way, that delta R is the correction factor for tree level. Therefore, this is exactly to be interpreted as our delta R. So in this notation, we get a prediction, a result for delta R, which is delta R is equal to delta alpha minus cosine square over sine square times delta rho plus small corrections. And that is the result. And here we get 6% effect, and here we get overall around minus 3% effect. And actually, if you do the calculation, then this amounts to around 1%. So it's not dramatically much smaller, but anyway, it is indeed smaller than the dominant corrections.
طيب نجد هنا نحن الجبال قلنا أن دلتا رو تزيد، وبالتالي مع زيادة الطاقة تزيد. لماذا؟ السي تربيع يساوي 1 والساين تربيع مع نقصان الزاوية. إذا كانت دلتا رو تزيد فهذا يعني أن سي تربيع أن الزاوية كوساين يزيد والساين ينقص، وهذا يعني أن الزاوية تنقص. نعم، الزاوية تنقص، يعني مع زيادة الطاقة فإن الزاوية تنقص. بالتالي يمكن نقول زيادة دلتا رو ونقول زيادة الحد أمام دلتا رو. الزاوية التي تسمى بالويك ميكسين تنقص، وبالتالي نرجع مرة أخرى إنه الدلتا زي أو الزي تقارب الدبليو بهذا. هناك تضارب، ربما يكون قلة فهم مني، أو ربما يكون هناك حلقات فاتتني، خصوصا حلقتين الفائتتين عندما يعني لم أسجل، لم أعلق، لأنه هناك كان أنا انشغلت بها، فربما يكون هناك أشياء فاتتني، لأنه هذه تعطينا أنه التقارب بين في هذه المعادلة تعطينا هناك تقارب بين كتلة الزي وكتلة الدبليو. وفي الاستنتاج السابق وجدنا أن هناك هو كبير بين كتلة الزي وكتلة الدبليو. فحقيقة لا أعلم حقيقة الموضوع. إذا كان هناك تقارب فهذا يعني ماذا؟ فهذا يعني أن كتلة أن الزي أيضا تذهب، الزي أيضا تذهب من الاعتمادات المجالية على الزمن، اعتمادات المجال الكهربائي على الزمن، إلى اعتمادات المجال المغناطيسي على المسافة، وبالتالي تقترب من الدبليو، أو العكس، أو الدبليو يقترب من الزي، لكن هذا أنا أراه بعيدا جدا. وإذا كانت تزيد الرو دلتا رو فهذا يعني أن كتلة الزي ثابتة، لا تتغير، ولكن الكتلة ال W هي التي تتغير وتذهب بعيدا وتنقص نتيجة لزيادة طاقة التفاعل، بالتالي تعطينا خاصية من خواص الثقب الأسود التي تقول لنا أن عندما تنقص المسافة داخل الثقب الأسود فإن الكتلة تنقص والطاقة تزيد، فنجد أن كتلة ال W تنقص. حقيقة يعني يحتاج أن العلماء يراجعوا هذه المسألة تحديدا ويعرفوا ما إذا كانت هذه حقيقية أم لا، أم تنتقد نظريتي، تنفي نظريتي أم تثبتها أو تتفق معها أو تدحضها. عموما أنا لو وجدت إجابة عميقة سأكتب ورقة علمية مباشرة في هذا الأمر إذا وجدت إجابة عميقة. إذا أيضا لم أجد إجابة عميقة سأجعل الأمر للمشاهد وللعلماء الذين سيشهدون هذه السلسلة ليقرروا هم.
So that is the result for delta R at the one loop level in the standard model, and you see the two effects. Indeed, muon decay is affected by the light fermion masses, by these large logarithms from leptons and hadrons, and it is affected by custodial symmetry breaking, and it is affected by some small corrections from vertex box diagrams and everything else. But that is it. And so let me just say that this can be used in the following way. So historically it was used, for example, to predict the top mass. Because we know that delta rho contains a term which is proportional to m top square. So it's quadratically depending on m top. Very strong dependence on m top. And of course, before the top discovery, the W mass had been measured. SW depends on the Z mass, so MZ, MW, E, and the muon lifetime had all been measured. Therefore, you can basically ask for which value of the top mass do I get agreement between theory and experiment, and then you do a fit, and the outcome was at the time top mass between 150 and 200 GeV would fit all the results, and then the top was discovered at 170 GeV. So that was really a prime example of electroweak loop calculations, and indeed that led to the Nobel Prize for 't Hooft and Feldman, where their main contributions are, of course, in the basis, like renormalizability of the standard model, invention of dimensional regularization, but they also did a lot, in particular Feldman, in inventing the rho parameter and putting forward these ideas to test the standard model and to do the predictions for such observations. So that was a big thing. And of course, after the top was discovered, one could put in the measured top mass, which is of course much more precise than 150 to 200, and then you can do the next step, namely then you see that of course also the delta rho depends on the Higgs mass. We didn't calculate it, but clearly it depends on the Higgs mass because there are loops involving the Higgs. And then you can do the same question one level higher up. What is the value of the Higgs mass for which you get agreement between theory and experiment? And so one has also predicted the Higgs mass before the Higgs discovery. And that prediction was actually not spot on the observed Higgs mass, but also not far away. It was a little bit lower than the observed Higgs mass. It was in the ballpark of 60, 80, 90 GeV, something like this, depending on the year one did this analysis. But the dependence is rather weak, and therefore one gets basically agreement again between observation and prediction. Of course, nowadays one is again one step further, and we can input all quantities because all the standard model parameters are measured very accurately, and in particular the Higgs mass is also measured to 1 per mil. And then basically inside of this delta R, everything is precisely enough measured. And we can go back and predict the W mass, because the W mass enters at 3 levels, so its role is amplified. And therefore we can now use this relationship to predict the W mass. We basically forget that the W mass is known, and we predict it from these relations. So the prediction depends on the Z mass and the muon lifetime, which is more precisely known than the W mass. And then we get either agreement or disagreement with experiment, depending on which experiment we take. If we take the particle data group value I gave you before, we get perfect agreement. If, however, we take the CDF value, we do not get agreement at all, but an 8 sigma discrepancy, which is a problem. So, but this is the thing. And
طبعا الأمر ليس بروبلم ولا أي حاجة، الأمر يعتمد على طاقة التفاعل. فهذا أولا يتفق مع نظريتي أن طاقة التفاعل تؤثر بشدة في هذا الموضوع. إذن CDF والهاي بارتيكل يمكن العلماء يبحث في هذا الأمر. فالطاقة هي التي طاقة التفاعل هي التي تؤثر في هذه العملية، وتكون نقطة ابتداء جميلة جدا جدا في هذا الموضوع. نقطة ابتداء جميلة جدا جدا، لأنه ستكون الطاقة مختلفة. نبدأ من هنا وننطلق. أنا في المراجعة القادمة بإذن الله تعالى، إذا يعني لم أنسى، في المراجعة القادمة سأحاول أركز على هذه القضية، وسأحاول أن هذه طبعا مدعاة لكتابة ورقة علمية بالمناسبة، لأنها بتعتمد على هناك فيديو أنا نشرته على قناتي، أنه لماذا لم يستطيعون قياس دبليو ماس بهاي أكيوريسي. ذكر لأنه الأمر يتعلق بالميون ولا النيوترينو، ولا النيوترينو ليست لديه يعني لا يستطيعون قياس كتلته بدقة. فهذه مدعاة للبحث حقيقة. بالنسبة لي أنا ذاتي هي يعني تشدني للبحث في هذا الموضوع، لأنه هناك اختلافات. أنا طبعا الاختلافات تشدني دائما للبحث. فهناك اختلافات بين CDF والهاي انرجيتيك بارتيكل ناتج من اختلافات الطاقة. فهذا موضوع جميل جدا جدا للبحث، والابتداء يكون بالطاقة، حيث أن هناك طاقة منخفضة وهناك طاقة عالية. جميل جدا.
And let me just end by saying, similarly, you can also analyze the structure of contributions to the other observables. Of our section 1.1, which were, for example, such observables like Z boson interaction with all kinds of fermions, where we define these various effective weak mixing angles, for example, sine square theta effective, and so on. And so for all of those, you can now do a similar calculation, and then you will discover again that also for those quantities, the effective weak mixing angle defined in an operational way, you will get corrections from delta alpha, delta rho in a similar form. So this ends our lecture on the electroweak standard model. This is just the beginning, but now I hope maybe some of you might be interested in going further. At least you are now aware of the ingredients, and you can follow either the literature or talks and summer schools and conferences and so on, or do your own calculations in this business. It is of course a very active field in the context of LHC experiments where we can do a lot of measurements of relevance, like the W mass measurement and similar measurements of electroweak quantities where such loop calculations are actually important. Okay, so thank you very much and have nice holidays and see you soon.
بهذا يكون قد انتهينا من هذه السلسلة. ربما يكون انتهينا من الستاندر موديل ككل، سلسلة النظريات تشرح الستاندر موديل ككل. صرنا هكذا أكون عملت فوق 70 فيديو. أرجو أن يكون هذه الفيديوهات هي ملهمة للعلماء للبحث في نظريتي. أنا يعني لم أكن دقيقا جدا في البحوث في هذه الأبحاث، لكن في مقتبل الأيام والسنين ربما أركز على دقة في هذه المعلومات التي قلتها. لماذا؟ لأنه ليس لدينا تجارب غير شيئين، يعني الأدلة التي في يدي أنا شيئين: الملاحظات والتجارب. التجارب هاي بارتيكلز، الملاحظات الكونية. فلهذا أنا قسمت نفسي بين الاثنين. فبدلا من أن أبحث بدقة حاولت أن أبحث باتر اللي هو النسق، التوافق في النسق، حتى يعني أعطي العلماء جايد لاينز بأنه يبحثوا في دقة المعلومات. فكانت السلاسل التي عملتها سلاسل كلها تتحدث عن النسق، فقط عن النسق، التوافق في النسق. هذه تزيد هذه تنقص، لكن بكميات كم تزيد وكم تنقص لم أبحث عنها بدقة صراحة، لأن كما قلت هناك تصارع صراع وصراع متناقض، وهنالك موازنات دقيقة يجب أن نأخذها في الاعتبار، وهذا يعطينا وصف دقيق للفضاء ثنائي الأبعاد. عموما قد تجدون هناك تناقضات بالمناسبة بين مقولاتي أو تعليقاتي في سلاسل وسلاسل أخرى، وقد تجدون تناقض في السلسلة الواحدة. هذا ليس لأن النظرية خاطئة، هذا لأنني لم أحسن التأويل في هذا الصراع، لأن هذه موازنات دقيقة جدا جدا بين الفضاء ثنائي الأبعاد والكتلة، ولازم نجد نضع القانون العام هو السيطرة دائما الفضاء ثنائي الأبعاد، وهذا ما يضمن الاستقرار دائما السيطرة في الفضاء ثنائي الأبعاد، خصوصا في التفاعلات دون ذرية. لا يمكن التفاعلات أن تهدم الكون مهما عملت، ولا يمكن أن تنشئ ثقب بس والداخل معمل ليتضخم ويهدم الأرض، لا يمكن يفعل ذلك. دائما الفضاء ثنائي الأبعاد هو المنتصر. فربما يكون هذه التناقضات جاية من هذا الموضوع. فعموما للعلماء يبحثوا في هذه السلسلة. أنا كده انتهيت من السلسلة الرئيسية، ربما ستكون هناك إضافات لأي تطورات حصلت في ما يخص هذه السلسلة، ستكون هناك فيديوهات إضافية للتطورات تضيف هذه السلسلة. لكن أنا عموما هذه السلسلة يعني قصدت بها أن تكون نظريتي نظرية كل شيء، وقد ربما أكون قد نجحت في أشياء وفشلت في أشياء، لكن العلماء يمكن أن يبحثوا في الدقة في الأشياء التي نجحت فيها، ويبحثوا عن تفسيرات الأشياء التي فشلت فيها. عموما هذا أكون انتهيت من هذه السلسلة. طبعا سأراجعها بيني وبين نفسي، لا عملت فيديوهات، لكن سأراجع السلسلة من خلال محاضرات المحاضر، ليس من خلال محاضراتي أنا، لأن أنا تعودت أنني لا أراجع الفيديوهات التي أنشئها، وهذه مشكلة طبعا أعانيها كثيرا، أنني لا أراجع الفيديوهات التي أنشئها حتى أربط هذا الفيديو مع ذاك الفيديو. لهذا تجدون كلامي مفهما بعض المرات وتجدونه يعني متناقضا، لكن في النهاية أنا هذا عيب فينا، أنا لا أراجع السلاسل، لا أراجع الفيديوهات السابقة التي أنشئها. عموما فسأراجع سلسلة الأستاذ إن شاء الله، وإذا وجدت شيئا في غاية الأهمية سأسجل فيديوهات وأعمل أوراق علمية بإذن الله تعالى. السلام عليكم ورحمة الله.